Hello, everyone. Hope this video finds you well. We're going to talk today about aromatics, anti-aromatics, and non-aromatics. Basically, the game we're going to be playing is that you're going to be given a structure. And from that structure, you're going to have to basically play the Hogwarts Sorting Hat game and figure out if the structure will fall under aromatic, anti-aromatic, or non-aromatics. So, full disclosure, right? I want you guys to kind of really, really pay attention to this and do a lot of practice problems because there's a lot of really weird, um, how do I describe this? Like gotcha moments, right? Where there's like certain types of like scenario geometry that will really, really screw up your day and really interfere with your ability to basically put the structure into one of these three categories. And so from all of these, right, um, just you're gonna have to just pay attention, right? And I would also say too, right, one of the ways that I kind of characterize this section of AB is that these two, right, aromatic and anti-aromatic, right, are basically going hand in hand. Whatever doesn't fall into any of these two categories, right, is automatically non-aromatic. Okay, so this is like you should go. Your mindset should be: are is the structure any one of these? Any one of these two? And if not, then it's going to here. If not, here. All right, cool. So let's talk about aromatics, right? So what are aromatics, right? They're a collection of very, very stable molecules. Every structure would love to be an aromatic, right? And so with that being said, right, there's some very strict rules as to who can be aromatic. And so the rules are, right, is that if in order to be aromatic, you have to follow Huckel's rule. You have to be planar, you have to be fully conjugated and cyclic, right? And so for Huckel's rule, right, that means that like whatever you whatever amount of pi electrons that you have, right? You need to be able to set that number, set the pi electrons that you have equal to 4n plus 2. And if you solve for n and n equals a whole number, right, then you basically are considered to be following Huckel's rule. From there, you have to be planar, which basically means flat, planar, basically the same thing. And you also have to be fully conjugated, which means kind of complicated, right? But it basically means that if you're able to participate in resonance, right? If these electrons, right, and your pi bonds, right, can participate in the pi system and basically bounce from bond to atom and atom to bond, right, in resonance, right, then it's considered fully conjugated. If it's cyclic, it basically means like, does it look like a cycle, right? Like, is it look like a Formula One race car track, right? Can you go into a circle around it? So yeah. So here we have benzene, one of the most famous, if not the famous, like the aromatic molecule, right? And so let's kind of go through this, right, and kind of see how benzene, right, obeys all these rules and therefore earns the lauded title of being an aromatic molecule. So one, right, let's follow the Huckel's rule thing, right? So 4n plus 2, okay? So let's count. 2, 4, 6. So for pi electrons, right, there's 2 for every single pi bond here, right? So 1, 2, 3, 4, 5, 6, right? Yeah. 1, 2, 3, 4, 5, 6. That's how I count. I don't count in twos. I just do this for the video. All right. And so there's 6, right? Let's set that equal to 6 and subtract 4n here, right? And you divide both sides by n, and you get 1. All right, cool. That's a whole number. So we consider this, yes, this aromatic molecule follows Huckel's rule. Second thing is going to be, is it planar? Is it flat? Previous experience tells us that if it's sp2 hybridized, right, then it's definitely planar and flat, right? So that works too. Third, is it fully conjugated, right? Well, in resonance, you can basically do this, right? You can basically move those arrows around however you would like. And so all these pi electrons are said to be participating in the pi system, right? And it can kind of bounce around, do resonance. So there I would say, yeah, it's fully conjugated. And for the most part, right, you can basically summarize this rule as like, are all of these sp2 hybridized? All the carbons sp2 hybridized? If the answer is yes, then it's most likely fully conjugated. Cyclic. Does it look like a Formula One race car track? Can I drive around in a circle around it? Then yes, right? If it was something along the lines of this, yeah, this is not cyclic, right? Not cyclic. Right? Cool. So cyclic, yes. So check, 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 check. All right. Huckel's rule, planar, fully conjugated, cyclic. Congratulations, benzene. You are aromatic. So cool. Lit. So let's go on to anti-aromatics, right? Basically, almost all the same rules apply, except for instead of Huckel's rule, it's 4n, right? And so let's go over this very famous example. Loki kind of forgot the name of the structure, but it's a square, right? So 4n, right? How many here? I count one, two, three, four, right? Or you can count by twos if you so choose. I don't personally. N equals 1. That is a whole number, right? And so yes, this follows the 4n rule. 2 is a cyclic. Looks like a Formula One racetrack to me, right? 3 is a planar. Yep. All sp2 hybridized. And by virtue of it all being sp2 hybridized, right, we can say that, yeah, it's fully conjugated, right? Because then it can participate in resonance. Alrighty, cool. And so, right, this molecule right here is, this structure right here is anti-aromatic. Okay, cool. So basically, anything that doesn't fall into these two categories will be considered non-aromatic, right? So I drew these two examples here, right? These are all sp3 hybridized, right? Just a regular alkane will never be anti-aromatic or aromatic itself. And on top of that too, right? While you may think to yourself, wait a second, this follows the 4n rule, right? Because, 2, 4. Well, um, this does not follow. You realize, right, that there's an sp3 hybridized carbon here, right? sp3. And sp3, right, means that it's not, it won't be planar, right? Because it has a 3D shape to it. It won't be planar and it won't be fully conjugated because you can't really do resonance with sp3 hybridized carbons. So therefore, all of these are going to be non-aromatic. Sorry, I paused for a second because I heard a bunch of noises in my kitchen. Hopefully, I won't get murdered. But anyways. If so, then I will go down teaching OChem the way I want to. So let's go over some examples, right? I'd love you guys to pause and try to figure out these examples for yourselves, right? And so, right, we're gonna go ahead. I'm gonna choose a different color for this, right? Yeah, this is my favorite color. Oh yeah, that's good. Right, cool. So let's quickly go through these, right? So pause the video and try to see if you can do it yourself. So for the first question here, right, one rule counts the number of pi electrons, 2, 4. Okay, cool. So this will follow the 4n rule. So this is potentially, right? This is potentially going to be anti-aromatic, right? That's one there, right? Okay, cool. Next thing, is this thing uh is this thing cyclic? Yes, it is. A 3, is this thing is it fully conjugated? I'm just going to abbreviate it as FC. Is it FC? No. And for those of you who are keen-eyed, this is basically the example I drew earlier, right? It's sp3, right? If it's not FC, then by implication, right, it means that it's not flat. Not flat either. So this is going to be uh non-aromatic. Sorry, buddy. You will never it will never be you. You'll never be him. Sorry about that. Anyways, so let's go move on to the second problem over here, right? Okay, cool. This is a very interesting system, right? It's like two benzenes flipped in and melded together. Very interesting stuff. Alrighty, let's rock and roll. Alrighty, cool. Let's count the number of pi electrons here. So we count 2, 4, 6, 8, 10. And just to triple check this because I suck at math, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. So 4n plus 2 equals 10, right? And let's quickly do the algebra here for those who can't really do it in their heads, which is totally fine, by the way, because I freaking suck at math. God, I hate math. That is a whole number, right? I have to stare at it for a second. Yes, it is a whole number. Okay, cool. All right, cool. 2, is it cyclic? In all intents and purposes, yeah. I mean, you can literally like the Formula One race car track, right? The do Max Verstappen, whatever. And so yeah, right. It goes around a circle. It's a cyclic thing, right? Yeah, I'd say it's cyclic. 3, is it fully conjugated? Yeah. Basically, every single carbon here is sp2 hybridized, right? It can participate in that pi system. Yeah. Okay, cool. So yeah, by fully conjugated, and then by virtue of that, right, it's flat. Flat AF. All right, cool. Congratulations, you have won the award of aromatic molecule. Let's go. All right, cool. Let's go over here, right? All right, cool. Let's count the amount of pi electrons there are. Two, four, six, eight. Okay, this will follow the 4n rule, right? This possibly could be anti-aromatic. Could be, right? Hold on, excuse me. Wait, hold on. Am I tripping here? Okay, no, I'm fine. I'm fine. Okay, cool. That equals two. All right, cool. Now the second part is it cyclic? I mean, yeah, it looks like it's cyclic to me, right? You can max for stop any way around that. Anyways, three. Is it fully conjugated? Well, let's find out. Hold on there. There's H's here. There's two sp3 hybridized carbons right there. So unfortunately, right, FC, that fails, right? And there, by virtue of that, it is not flat. And so because of that, right, unfortunately, we're gonna have to bestow the very unfortunate title of non-aromatic. You were just a normie to us. You are not special. Get out of our faces. All right, cool. Moving over here, yeah. So one, right? Let's count the amount of of pi bonds here, right? And so yeah. So as you can see here, right, there's a plus charge here. There's some weird like gotcha trivia moments, like aha, we got you now. Uh, exceptions when it comes to ions, and especially if there's lone pairs, right? So this is basically the start of the bullshit section. So brace yourselves. This is gonna be kind of rough. But anyways, let's count this, right? Two, four, six. Okay, right. So 4n plus 2 equals 6 here, right? And that plus charge obviously doesn't have any electrons on it, right? Because it's electron poor. So we don't have to do anything about that. Right. Okay, lovely, right? That works out. That is potentially aromatic, right? 4n plus 2 rule works, right? And so from here, right, let's move on. Is it cyclic? Yeah, cyclic to me, right? No real logic there. Just kind of have to feel it out. Now, three, here's the kicker, right? Is it fully conjugated, right? Now, the question is, right, can I participate in resonance here? Yeah, I can. I can move that there, right? And we can end up with this here. Oh my God, that's not what I want to do. We can end up with this here, right? We can move that plus charge over here if we wanted to, right? And so if it's fully conjugated, right, generally means that it can participate in resonance, right? So fully conjugated, I'd say so. Yeah. Ooh, now is it flat? Now, this is going to be a very, very long-winded tangent, but I'm going to give myself a little bit more room here for this tangent, right? But do you guys remember, right, when we were reviewing SN1, right, or from Organic Chemistry 8A, right, that if you took something like this, right, Br, right, and if you're doing an SN1 reaction, right, this popped off onto here, right? There's a plus charge here now, right? The reason why, right, you end up with a mixture of different types of isomers, right, or stereoisomers, right, is because of the fact that it's flat, right, and a nucleophile, right, can attack from top or bottom. Now, because of that, right, this plus charge, right, the presence of a plus charge in this case, right, would mean that it's flat. And so, yeah, I would say it's flat. Congratulations, you are aromatic. Okay, cool. Let's move on over here, right? This is where more of the bullshit intensifies. Okay, cool. Right, the immediate problem now with um, lone pairs, right? You know, the question is, do we count it when we are doing, do we count it when we were doing the counting for pi bonds or for pi bonds, right? And pi electrons. Now, the answer, right, um, will probably piss you off because it pissed me off when I first learned about it, right? So, as you can recall, right, we're counting pi electrons, right? And pi electrons, right, are able to do resonance, right? They can jump into these different pi orbitals here, right? Now, as I just drew right here, right, these lone pairs fall outside of this pi system, right? It can't really jump into here like this double bond can jump into here, right? And so with that being said, right, right, this won't count, right? And why? You can just sum it up as bullshit unique geometry. Lame. AF. All right, cool. So we're not counting those that lone pair on that nitrogen, right? And so yeah, I'm gonna go ahead and I'm going to regard this, right? Let's see, right? One, two, three, four, five, six. Okay, cool. Even with those, without those lone pairs, right? You got this, right? 4n minus 2, 4n equals 4 here, right? And then from here, right? N equals 1. And then we can quickly breeze through the rest of this, right? Cyclic, yes, yes. 3, is it fully conjugated? Yeah, great. It's able to kind of go around and there's no atom here that isn't doing any of that sp2 stuff, right? Uh, this, right, these lone that this bond right here can jump into this bond right here, I'll draw right here, can jump into one of these pi bonds if it wanted to, right? So that's cool there. That's chilling, right? It's fully conjugated, I would say, right? And 4, right, is it flat? Yes, it is. So this gets the awesome title of being aromatic. Now let's immediately go over here, right, where we are unfortunately, I'm gonna move, I'm gonna give myself more space. That I can't. Whoo, man, I'm gonna do that. Move this down here, right? Um, we're gonna immediately break that rule. I'm so sorry, right? So let's kind of go over this again, right? So now we have a really weird situation here, right? Where you potentially could count those lone pairs, right? But let's kind of talk about it for a second, right? So, um, essentially, right, let's kind of draw that pi electron system again, right? Do-do-do, do-do-do. As you can see here, right, the presence of an H, right, has kind of pushed the lone pair up into the system of orbitals that can participate in. So now it can participate in resonance, right? And so with that being said, we can count that now, right? So 1, 2, 3, 4, 5, 6. 4n plus 2 equals 6. Let's sort this out, yeah? Let's sort this out. Equals 4, 4n, n equals 1. Lovely. Okay, alrighty. So it's fully, not fully conscious, sorry. It is going to follow the Huckel's rule 4n plus 2. Alrighty, cool. So if you're confused about the difference between 5 and 6, right? Um, we'll summarize it as this, right? If you have something along the lines of this, right? If you have some sort of weird unknown, right? I was gonna put U, but U stands for uranium. That'd be weird. So let's say you had a system like this, right? And you had lone pairs here. Don't count these, right? But if you had something else, right? Like let's say for example, right? If you had a hydrogen, right? Or if you had a situation, right, where or if you had a situation, right, where you had another lone pair, right? Then yes, you would count both these situations when you're trying to do the Huckel's rule for n, right? So that's the shortcut that I basically use, right? All right, cool. So let's move on, right? Is it cyclic? Yeah, I'd say so. Is it fully conjugated? We just had a huge tangent about that, so yes, it is fully conjugated, right? It can go and do resonance without violating the octet rule, so that works. Flat, I mean, yeah. So congratulations, you are aromatic. Alrighty, let's move on to some more examples over here, right? Okay, all right. So let's go ahead and figure this out over here, right? This is an example we used earlier. We can just quickly do this again, right? Is it 4n plus 2, right? 2, 4. Oh, actually, no, it's 4n. 4. N equals 1. So this is possibly anti-aromatic, right? So 2, is it cyclic? Yep. 3, is it flat? Sorry, is it fully conjugated? Yeah, it would say so, right? This is one of the examples we used earlier, right? This is you can do resonance throughout here, right? And by virtue of that, right, it's flat, right? It's flat. You can do that. It's flat, right? Because remember, right, having a plus charge there, right, is similar to having a situation where it's SN1, right, where you can attack from the top or the bottom and get a mixture of stereoisomers. Right, over here, right? Let's do this one more time, right? This is 4n equals 4, right? 2, 4, n equals 1. And then from there, right, we'll have, is it cyclic? Yes. Now 3, right? Is this fully conjugated? Yeah, I'd say so, right? And by virtue of that, is it flat? Yes, it is. It's following the 4n rule, so that means that this is anti-aromatic. And I just realized I forgot to give a this is also anti-aromatic. Not exactly aromatic, but hey, at least you're not on non-aromatic, right? Woo. Good times. Let's move on over here, right? Where, we have a very interesting scenario here, right? So do we count these lone pairs here, right? And so remember the rule up here, right? If there's something else that's there, right? If there's more, if there, gosh, yeah, if there just is one lone pair there, don't count it. But if there's a lone pair and something else there, like another lone pair or like an H or something, then we count it, right? So we're gonna go ahead and we'll count this, right? 2, 4, 6, just from those, right? So 4n plus 2 equals 6, right? And n will equal 1. So that follows with 4n plus 2. How exciting. This could potentially be an aromatic. Congratulations, little structure over here. Is it cyclic? Aye, aye. It's fully conjugated? Yes, sir. Is it flat? Yes, sir. Hook, line, sinker. Congratulations. Woo! Aromatic. All right, let's move on over here, right? 2, 4, 6, 8. 4n. That will follow the 1, 2, 3, 4, 5, 6, 7, 8. That will follow the 4n rule, right? N equals 2, right? So this is possibly anti-aromatic. Aw, so sad. Cyclic. Yes, sir. 3. Fully conjugated. Aye, aye. 4. Is it flat. Hell yeah. This will be anti-aromatic. All right. Now here's another very interesting scenario here, right, that you'll encounter. So we can go ahead and kind of quickly dust through this, right? 1, 2, 3, 4. I count 4, right? So 4n equals 4. This is possibly anti-aromatic. 2 here, right? Is this cyclic? Yes, it is. 3 now. Is it 3? Is it fully conjugated? Hmm. Is this fully conjugated? Hmm. Very odd. Well, right? Um, as you can see here, right? Let me ask you this, right? What's the hybridization of this nitrogen right here, right? I'll give you guys an example, right? Or take some time to guess, right? So just like the fact that if you have a CH4, right? A CH4, right? The CH4 has a 3D structure, right? And it is sp3 hybridized, right? Very similar vibe to this nitrogen right here, right? So unfortunately, right, since this nitrogen has four things attached to it, similar like how this carbon is, right? Then it is going to be sp3 hybridized, in which sp3 is not fully conjugated because now you can't really do resonance with that, right? On top of that too, right, it is not flat. So not this, not that. This is going to be non-aromatic. Sorry about that. Okay, cool. So this is basically the naming game, right, of the categorization game of non-aromatic, anti-aromatic, and aromatic, right? Let's go all the way down here, right, to the logic of aromaticity in action, right? So why does aromaticity matter, right? Well, since remember, keep that rule in mind, right? That general idea that structures love aromaticity, right? Just like how everybody who's in college right now would love to have $1 billion, right? Or maybe some people wouldn't, I don't know, for whatever reason. Or if, people who are in bodybuilding, right, look up to the guy or the girl or the person who's just the buffest, right? Structures would love to be aromatic, right? And ideally, right, if you had $1 billion, right, you wouldn't want to lose it. Same vibe, right? If you were already aromatic, right, you would not want to lose your aromaticity, or vice versa, right? If you had a chance to be aromatic, if you had a chance to be a billionaire, you take that, right? 110%. I would too. Um, so, as you can see here, right, this structure right here is non-aromatic, right? initially at least. But the thing is that the structure is pKa, right? That means how well of it, how good of it being an acid, right? Or rather, is it acidic, right? Does it love giving away its H's, right? Right? Is very, very low, and therefore it's a really good acid. Why is that? Right? Let's do a quick proton transfer and let's kind of explore this idea. Why? Right? If I grab this H right here, right? I end up putting a negative charge there, right? You're going to end up with this bad boy right here, right? And we agreed before, right, that it was non-aromatic because there was a sp3 carbon there, right? Well, right, let's run this through again here, right? So 1, right, is it 4n something, right? 1, 2, 3, 4, 5, 6. Yeah, right. Remember, it follows that little rule of thumb that I gave you, right? Where if you have a lone pair and something else there on the same carbon, you count that lone pair when trying to account for 4n plus 2 or 4n, right? And so, right, 4n plus 2 equals 6, right? And so, right, we're going to go ahead and we're going to quickly kind of do this right here, right? So, n equals 1, 2. Is it cyclic? Yes. It's fully conjugated? Yes. Yes. Is it flat? Yes. And my iPad just crashed. Dude, I was like a minute away. Good Lord. So close. Let me go ahead and reshare my screen real quick. Hold on. I was also doing a big reveal too. What the heck? That's not cool. That is not cool at all. Not cool at all, good dude. Anyways, but yes, this is relatively flat, right? It's not sp3 hybridized, right? So yes, this is flat. So no wonder, right? This structure right here, whose name I forgot, is a good acid because, right, it has a chance to give away an H, right, to become aromatic, right, and to fulfill its dream. So essentially, all this molecule has to do, all the structure has to do, is to be a good acid, and it will become aromatic. It'll become more stable, right? So is essentially right. Hopefully, you can kind of see the logic here, right, of how aromaticity, right, can affect chemistry. That if you have a chance, right, to give away an H and to become aromatic, increase its aromaticity, right, then it will do so. And that is the logic behind why this structure right here, right, is a good acid because it will give away its H, right, and become aromatic. And so hopefully that was helpful. Aromaticity has a bunch of, there's probably like a couple more scenarios that I haven't accounted for, but please just study diligently and you'll be able to get those. Alrighty, thank you, and hope you guys have a good day.